Good morning, everyone. Welcome to GA. I've got the pleasure this morning of introducing Dr Ole Nielsen. Ole has a graduate degree from Denmark in Maths and Computer Science. He's a PhD in Scientific Computing from the Technical University of Denmark. He's a postdoctorate fellow at the ANU from 1998 around large-scale data mining and tools for ANU supercomputing facilities and bioinformatics. He started with us here at GA in 2003. He's a pioneer around parallel computing. He developed inundation models and led GA's tsunami risk assessment program. He was awarded in 2008 for outstanding focus on software quality and science capability. He pioneered the use of open source as a mechanism for collaborative software development, and that's going gangbusters at the moment. And he was selected as numerical modeller for the team establishing the Australia-Indonesia facility for disaster reduction in 2010, which involved volcanic ash dispersion modelling and real-time earthquake impact systems. He returned to lead the centralised software development capability in 2013, first as development manager, then as director of software development. So Ole today is going to talk to us about scientific method in software engineering, value adding to scientific outcomes. Thank you.
Thank you. Well, thanks for those nice words, Anthony. It's a great honour. It's a great pleasure to be part of this change at this time in this agency. And it's with great pleasure that I share with you today some of my thoughts around scientific method in software engineering. So Jane Sexton, she pushed me hard in April to give a Wednesday seminar. And not really knowing what I was going to talk about, I thought maybe we should talk about stocktake 2 years of centralisation, where we're at. But then when she actually sent the advert out, there was a new title, Scientific Computing, Scientific Method in Software Engineering. And I thought that was a much more interesting title. So I quickly scrambled together to realign myself with that thinking. So thanks for that, Jane. I'll be talking about just 4 things. First thing is what is scientific computing? It's used a lot in the agency this sort of past 6 to 8 months, and there are various opinions perhaps of what it might be. So I thought I'd give my first crack at what we could use, how could we define that. Then I'll talk about the needs in Geoscience Australia as I understand them from the 9 branches, and I'll talk about what it all means for software engineering, the scientific method. And I'll talk about the future directions as I see them. So what is scientific computing? The first thing to do in my mind is look at it globally. What could it be? So I'll just paint a picture by going through some various definitions. And I don't expect anyone to read the fine print, but the slides will obviously be available for that later. So the first thing to understand is that scientific computing goes by many names. Computational science is another completely equivalent term. I think it just depends on whether it's scientists doing computing or computing people doing science, pretty much. So when you start looking for computational science, Wikipedia is obviously a place to go, because if you don't agree with what's there, we change it. There are 3 groupings here. Numerical simulations, for example. And they talk about understanding known events like earthquakes, tsunamis, and other natural disasters. That's very close to home. That is certainly an example. Predicting future observations like in weather forecasting, as the Bureau is doing. A lot of model fitting and data analysis, that would include gridding and tuning models, right, to understand phenomena we observe. And then there's optimization, which is machine learning, statistics, time series analysis, things like that. So just looking more sort of globally, I've found a definition here from the Institute for Computational Engineering and Sciences in Texas, and they compare computer science and computational science like this. Computer science includes all the things we do on our computers and how we build systems to do those kind of things. Computational science is about the application of computers to advanced science, largely in the modeling and simulation of the physical world. Another place to go is MIT in Boston. They have a computational science course here led by Gilbert Strang, who's probably one of the best lecturers I've ever seen in my life. You can look him up on MIT's website and see some of his lectures. He is listing some topics there that he sees as core to computational science. And I'm not going to read them out, but they are some of the disciplines we're talking about that are in use here as well. My former supervisor is now director of the Scientific Computing Center at the Technical University of Denmark, and I'm going to have some beers with him in July, and I'll pick his brain a lot, I think, at that time again. He defines it as the science of using computers and mathematics to solve problems from science and engineering. Our partners at CSIRO, they have a scientific computing group and they have a training program, and they talk about various things to do with HPC, which is part of scientific computing, and they also talk about floating point number considerations. It's sort of a maybe little understood part of scientific computing, and I will actually spend 10 minutes in this talk giving some examples of problems that arise from floating point inaccuracies. Society of Industrial and Applied Mathematics, for example, they have a whole conference on computational issues in geoscience, and you can see the examples here are underground waste disposal, hazardous waste, earthquake prediction, weather prediction, global climate change, things like that. They actually have a whole journal dedicated to scientific computing from this SciAm, and they're talking about methods, algorithms, software, and high-performance computing. So these are places we can go and look to understand what scientific computing is. The final example here is there's a whole Springer-Verlag journal on computational geosciences. And again, you can see the numerical methods they are listing there and the areas of applicability. So there are plenty of sources to understand what scientific computing is. So if I was to characterize it, first cut, absolutely first cut here, it would be something that's concerned with the laws of physics and units of measure. So it's not banking transactions, for example. It's not web delivery. It is something that works with meters per second, gravity, density, things like that. It is something that's subject to validation and peer review, which is what the scientific method has always been about. And obviously the open source that Anthony mentioned is one way of facilitating that. And as was mentioned by the CSIRO training course, rounding errors, the IEEE double precision rounding errors and numerical stability are things that scientific computing professionals need to deal with and certainly be aware of. It is about implementing scientific statements, and that means subject to falsifiability and peer review. And I'll talk a little bit more about that and the link between falsifiability and testing of software. And often scientific computing requires high performance computing, but not always. Time series analysis, for example, we use a lot. They are 1D problems, very fast. You don't need HPC for that, but it's a typical enterprise. It's typically based on mathematics and statistics, as we see, and typically relying on large and interoperable scientific data sets. So there's a strong link to that as well. So examples, obviously, numerical modeling and simulations, as we see in natural hazards area, perhaps in the future in reservoir modeling in oil and gas exploration, for example. Data fitting and gridding, as we see in LiDAR data, turning that into grid products. A lot of inversion. We saw Phil Cummins talk about reverse time imaging to invert for tsunami sources, for example, recently. And of course in earthquake and geophysical exploration, that is key. It is machine learning and statistics, and increasingly quantifying uncertainty by doing probabilistic modeling to understand how sure we can be of a result, how much can we trust it. And I see Jane smiling there because I got that from her. There we go. So I've had some very cursory, quick chats to the branch heads around their thoughts about scientific computing needs. And I'm not going to read them all out, but they will sort of form the basis of going forward in identifying or painting a picture of what the needs are. But there's a lot of commonality here around inversion, around forward dynamic modeling, around uncertainty, probabilistic modeling, and of course gridding and inversion, and many, many more things. But many of the disciplines behind that are quite similar. And I think that is one of the things we'll find, that there are similar generic skills that are applicable to many of these things. And I apologize to the branch heads if these are not accurate representations, because this is very, very first cut. So thank you. So let me just run through a simple example. It's very, very hard to explain numerical instability and rounding errors. But I found an example that is fairly simple with some pictures so we can see what it looks like and where the dangers are. So it's the simple case of finding the geometric centroid of a polygon, a non-self-intersecting closed polygon with n vertices. And that's the centroid, and that is a fairly simple, straightforward formula that will take all the vertices, the longitude and the latitude, x is longitude, y is latitude, and subject them to this formula, and divide by the area, which is defined by that, and you'll get the coordinates for the centroid. And that is fairly simple to implement. But I'll show you what happens. So this is, of course, a real-life example that I experienced firsthand and fell in with both feet first, and I'll be happy to admit that. So applying this formula to polygons at the level of a city, and in this case the Jakarta Regencies, provides the perfect result, and it matches perfectly with centroids generated by Esri or other tools, and were indeed part of a unit test suite for this code that were embedded in our hazard impact modeling system, and it worked really well. Then, of course, applying it at a finer scale to buildings, at the building level, it's not quite right. It's certainly not something you would be able to trust. And the question is, why is that? And I guess your guess it's to do with rounding errors, but I'm going to show you how that happened. And the hint, obviously, is that the errors are very much east-west rather than north-south. So there are a lot of hints there in what could happen, but I'll just take you through how you discover the problem here. So first thing to do, and so why do I have a lion there? In mathematics, there's a concept about catching wild lions, and you do that by using tame lions. And this is a tame lion, lots of tame lions. And anyone who has studied things like this Taylor series expansions or Fourier series expansions will know that you can represent a complicated functions through a combination of very simple functions that you can understand, whether they're polynomials or cosine or sine functions. And that allows you to do things you couldn't otherwise do. In this case, and this is absolutely the best advice I ever got from my supervisor back in the day, was don't attempt to understand the complex problem until you understand the simple equivalent first. And the simplest equivalent here, the tame lion, is a square, 10 by 10 meters, put in this location, so we can start understanding what the problem is. And 10 meters is this many degrees in this direction, and this many degrees in this direction at that location. So therefore, it's easy to work out what the expected centroid is. Divide this by 2, divide this by 2, and plug it right in, and you get the expected centroid here in degrees, longitude, and latitude. No problem. Then we take these 4 corners, and these are the coordinates, and plunk them into the formula. And you get this centroid, which is about out there. And if you subtract these two and calculate the error, it's 10 to the minus 4 errors in the longitude and a bit less in the latitude. And converting that back to meters, so 100,000 meters is about 1 degree. You get an error about 21 meters, which is a lot for a building, quite a lot. All right. So the way to understand that is to do what's called an error analysis, quick and dirty. What you do, you go back to the formula and stick in. You say, well, let's assume that the error here is almost negligible, 10 to the minus 14th in this term. And then we start applying the formula on paper. We say, all right, let's multiply this error by 212, and we got 4 corners. So in scientific computing, you always start from 0 to 3, not from 1 to 4. That's one hint. And you multiply by 4 here, and that gives you a value of 10 to the minus 11th of this whole term here. Then we need to divide by the area, which is 10 to the minus 8 of this building, of this square. And that is the same as multiplying by 100 million. So now we are amplifying the error by 100 million. And 10 to the 8th times 10 to the minus 11th is 10 to the minus 3. Now it's getting big. And of course now converting that to meters by multiplying by 100 million gives you an order of magnitude of 100 meters. So it's quite clear what's happening here. We are amplifying the error by a number that's too large. So what is the medicine? What is the problem here? The problem is that the late 19th century, the Royal Geodetic Society of England decided to put the meridian in London. Now, if they had put that in Jakarta, it would have been sweet. And of course, but then there would be problems in the US. So therefore, what you do there is called normalization. A very common technique. Of course, it doesn't help with a lot of other problems, but it's a classic technique. We put a meridian for every polygon where we need it. We just put it where we need it, and we can do the same for the latitude, and then we scale. That's called normalization. We scale, so every number here is somewhere between 0 and 1, and the error amplification is going to be a lot smaller. So it's just a simple example of the kind of thinking you sometimes go through as a scientific computing developer to make sure that you don't amplify errors and run into uncharted territories. So that was a little example. Now, using those normalized coordinates, of course it's smack bang what it should be, and matches the results from the other tools as well. No problem. And it's a very cheap and inexpensive operation. It's not a problem. Now, numerical instability is then the next step. Now imagine, so the definition of numerical instability are algorithms that amplify small errors in the input. Small errors in the input are amplified. And if that happens over time in dynamic simulations, that can be detrimental to the solutions. And typically it'll either create solutions that are 10 to the 38th or something like that, like huge numbers that swamp any meaningful number, or it can be oscillations that are numerical and not real. And it's very elusive, because when you run a numerical code like that, it might look perfectly okay for a while, and then suddenly things get a little bit bigger, and suddenly it's exploded. And you can't really pinpoint when it happens. So the only way to solve it is a mathematical analysis of the algorithm to understand what is happening, just like what I was doing before. But there are many other techniques. You can't just look at the code or look at the solution. So it's something you can never ignore. Even if you're using other people's codes, you need to be aware of this problem. So moving on to test-driven development, which many of you have heard me talk about a lot, but I think it's a very important part of scientific computing to actually make sure that the decisions we make actually are informed by real science and not just by spurious bugs or numerical instabilities. And I'm just putting this in. We're supposed to test it before we build it, which is a bit difficult when you're a mouse there. But it's very important to test before you build. So the scientific basis for this, and I'm going out on a limb here, but Karl Popper, a very famous philosopher, he wrote in 1963 a seminal paper called Conjectures and Refutations, the Growth of Scientific Knowledge. And in that paper he stipulated what a scientific statement is and how you can verify if it is actually valid or not. So a statement is scientific if and only if it's falsifiable. So for example, if I was to say gold is soluble in hydrochloric acid, and if you have some spare gold, you can then go home and put it into hydrochloric acid and realize that it's a false statement. It's a scientific statement, but it's not true. So it can be falsified, and therefore it's scientific. If I was to say some herbal medicines are beneficial for my health, that is probably true, but it's not a scientific statement. It can't be falsified, because I said some. Now, the equivalent in software engineering is that the source code really reflects the theory about a particular problem, and the tests we write are the attempts to falsify that theory. And that is important to understand, that that's what we're doing. And that means we're not proving it's correct, but we're saying if it fails, suddenly there's a problem, we need to fix it, we need to change our hypothesis. So the way to do test-driven development is to start thinking about a new feature or a new thing we want the software to do or predict, and we write a test for it where we say, if we present this input, say here are some polygons, and we know what the centroid should be, we say, all right, let's verify that the expected output is this. And we code that up in the software, and we run the test, and it will fail because there's nothing behind it. So we'll always go down this path. Then we write the code, run the test again, and it may still fail. And we cycle around here a bit until it passes, in which case we run all the tests for the rest of this whole system to verify that it still works integrated, but also that it hasn't broken something else invariably elsewhere in the system, because that is a real danger when you make any modification. And then if that fails, we go back to square one, and if it passes, we integrate, and we're ready, and we do the next one. That is the basic principle of test-driven development, and a very important scientific way of operating. And I'll give an example that some of you have seen before. It's 10 years old, where we tried to falsify the hydrodynamic simulation code we wrote 10 years ago. And the example we're using here is a particular event that happened in '93, where an earthquake created a tsunami at Okushiri Island in Japan. And the observation there was one valley that had a 32-meter run-up. The highest point that got wet was 32 meters. It's not a wall of water. The highest point that got wet was 32 meters. Just nearby, and the rest of the coastline had about 10 to 15 meters, much less. And nobody really understood why at the time. A wave tank experiment was set up in Japan that did a 1 to 400, I believe, scale experiment to actually see if they could recreate this run-up, and they did. And the beauty of that was they collected all the data necessary to validate or indeed falsify the numeric codes. It's become a benchmark. So I'll show how that works. So here's the output of the hydrodynamic model, so using this example, and this is Monai Valley. So just watch this place and watch this part as well, and I'll run it forward. First we have the drawdown of the tsunami as the trough precedes the tsunami. Then he moves in, and we have a reflection from the north, and we got constructive interference with the main wave, and we got shoaling, which is the amplification of the wave as it enters shallow water, and then we see the run-up driving right up there, 32 meters. And the good thing about modeling is you can go backwards and just see it again what happened. There we go. And that explains it. But of course that also leads to a really valuable data set for validating the code. So what we did, we compared the observed, which is the blue, to the modeled waveforms at these three gauges there. And you can see that apart from being very flat in the beginning, because the real water was just sloshing around, and you can't get that to sit still without freezing it. So there was a bit of sloshing around there in the beginning. First thing you see is the drawdown, very distinct and very sharp edges, which is a hard thing to obtain in a numerical code, because that's where numerical instabilities often arise, because you divide by very small numbers. And then you get the first reflection, second, third, fourth, and then it sort of peters out. But a very, very valuable data set and a very, very good validation. And it does not prove that this code will work for a lot of things, but it falsifies it. If this test fails as a result of a change in the future, we will know immediately, and we can say that's a problem. So this test is still running 10 years down the track, and I can sleep at night knowing that the important features of this are still in place, no matter what other people are doing to the software. And that's the importance of it. So that's why I like to say a bit flippantly that if I had the choice of throwing the software away or the tests, I would just throw the software away, keep the tests. They are the valuable bits. You can always write the code again, if you've got a bit of time. And this one is then part of another 1,000 tests that are testing other things, right? And by running them all automatically, you can always verify that together they all pass. So you have more confidence in your software. More confidence. You don't prove it works, but you have more confidence in it. And that's straight out of Karl Popper's theory. Now, I think Trevor Dew is in the audience. There he is. Yeah, I had to put this in. So what happens with software that doesn't have a test suite? It still looks like the original software, but you can trust it less and less, and it starts growing little errors that you might not notice until you start driving it. And this is a piece of backyard junk, which was what Trevor Dew, he coined a piece of software once that didn't have a test, an untested piece of backyard junk, and that's what it is. A similar example that I just threw in last night, because there's a court case right now about some software that was embedded in the Toyota Camrys. It's a little bit different, but it's still very important. What happened there was a woman was driving her Camry down a ramp from the freeway and hit the brake, but the software governing the engine kept the accelerator going. And she ended up pulling the handbrakes and made some very long skid marks, 105-meter skid marks, before crashing the car into this dam there. And the court case was hearing the software underneath this, that it had 100,000 global variables. And what that means is that everything in this system is dependent on everything else, right? And that is why we talk about low dependency architecture. So obviously it needs unit tests around it to verify it's correct. But if it is not, if a change in one part of the system will affect every other part of the system, it is very, very difficult to develop it forward. And the 10,000 global variables is a case of high dependency architecture and what can happen as a result. And this was in the court case, so it's not just an academic exercise. And so I just said, so if we have spaghetti code, high dependency architecture without tests, we cannot use it to make decisions. And this is the repository where we should put it until it has been fixed up with tests around it. So enough of that. Test-driven development, together with automation, low-dependency architecture, and cultural change, lead to a very, very interesting concept in software engineering called continuous delivery. And I'll just talk a little bit about that, because it's a direction we are pursuing. And I borrowed these slides from a lean software engineering workshop I went to in December. And it talks about a complex system, like the Australian tsunami warning system, or indeed many of the things we have here. If you want to make a change to that, and if that change is big, it is very likely to cause problems or breakages. A big smash is very, very difficult to recover from in a complex system, whereas small guided changes subject to testing and validation with the ability to roll back are far more stable. And this is the sort of wisdom of continuous delivery, that if you want to keep it stable, you make small changes in the right direction and make the next change guided by what you just saw. This is how science is developed as well. And this is how the agencies are starting to think. The Bureau, for example, I borrowed this slide from Joe Pitt from the Bureau. They're talking about changing their team structures, the way they work. Instead of having a separation of roles in development, testing, and release and operations that invariably have to wait on each other and invariably have different priorities, right? They instead put all these functions into small teams that are multidisciplinary and far more agile, far more able to release to production rapidly and frequently. And it's not about, it has to be fast. It's about being able to do small things frequently and quickly realize if they are in the right direction or not. So this is not just us talking about it, they are talking about it. Australia Post, there's been a lot of talk about that. They came here 18 months ago and talked to us about their transformation. The past 2 years they have transformed the way they do application development and deployment dramatically. They have embraced the continuous delivery philosophy, and they created multidisciplinary teams. And by that we don't mean teams where people are different necessarily. We're talking about teams where every team member had the ability to do multiple functions. Some might be better at one thing than others, but everyone has the ability to step in and do the other's function to help each other out. That's one of the things. They have created an inclusive culture where it's safe to experiment. And of course we all know the theory said that leads to innovation. That is very much the message of the inclusive culture we are hearing at the moment, and I think there's a lot of evidence for that. They can iterate and release more often, and more importantly, they focus on value creation for their agency rather than small intermediate goals. They say they have better experience. Their users have better experiences and they are delivered more often. And of course, with this pipeline and underpinning that is all the test-driven development and quality that makes it robust. So the results, as they have measured, all their applications are in Amazon Web Services, which is a cloud provider, the biggest cloud provider there is. They deploy something like 500 full stacks per month. And a stack, what does a stack mean? A stack means everything from the virtual machine through all the layers up to the application. Everything in one hit, fully automated and scripted, and deploy that per month. They have identified a time and cost saving of deployment of 95%. They have 5, what they call them DevOps people, supporting 120 developers. They're very large. They have brought deployment down from 9 days to 15 minutes. They have consistent environments. The spending is operational and variable depending on demand rather than capitalized and constant. And they found that is saving them resources. And most importantly, the teams working here, they self-serve. They don't wait for someone else to provide something for them. And that's a very important thing they have achieved there. So this is just my mind map of how these software development practices hang together. And I have mentioned most of them, but this is how I see it. For every mind map like that, there are hundreds of different ones that are equally valid. This is just how I see it. that the test-driven development I talked about, together with automation, lead to an automation of this integration process. Combine that with the portability of software that you get from low dependency architecture and open source, and combine that with cross-skilled teams, give you the ability to continuously deliver features. And that again leads to systems that are more maintainable because there's less room for human error. They're reproducible because they're automated, and that's of course a very scientific value, reproducibility. Frequent validation, that means the scientists can quickly get validated whether this idea was a good idea or not, so we can fail early if we are on the wrong path. That leads to increased stakeholder engagement because you actually don't have to wait 9 months to see if this was a good idea. Time to market as a side effect is reduced. We got more visibility and transparency, and from all of that I argue we also get better security potentially by having it like this. So, the future in this area is that we are going to come up with an agency-wide scientific computing strategy that is something we own collectively, that will paint a picture of what this looks like for us in the future. And the sort of timeline for that is we're planning to have a draft in place by December and get that out to everyone to tear apart and comment on and give input to, with a view to have something finished by this time next year perhaps. Initially, we get a terms of reference ready by the 1st of July. Got to get very busy there, but just to kick the ball off. And what we propose here is to convene a working group with representation at the ground level from all the branches, people who work with this in their daily life, to inform what's needed. We need collective ownership of this. So it's very much an agency strategy we're proposing. It would need to define scientific computing a lot better than I tried to do before, but come up with a robust definition that makes sense to us. It really needs to look at what the other science agencies are doing, both in Australia and globally. It needs to identify very clearly what our needs are as we understand them collectively. And then it's a matter of mapping what skills are then needed. Like, where's the communality? Where are these generic skills that can move and support maybe 1 year in this area, another year in this area, and be portable, and therefore actually getting a corporate sort of visibility of the whole landscape, and be working where they add the most value. And that will then inform workforce planning going into the financial year after next. Alongside that, in parallel with that, we are also trying to embrace a continuous delivery capability. And we have been very fortunate that Australia Post, the Digital Delivery Centre, who just undergone a transformation, have agreed to pay the salaries of 4 people to come down for 3 months and embed themselves in the culture and really get to understand the details of this so we can learn from it. And that is, I see that very much as part of the ICT transformation, the cloud delivery, cloud readiness need, that we can be informed by someone who already made their own mistakes. And they have a lot of gotchas as well that we can learn from. And then in parallel with that, not just 4 people, we need to generate some training for the rest of us in the scale. It's called the Scalable Agile Framework, which is what they used. And if we like what they did, we could get some training here as well, so that the rest of the agency is ready for a change in the way we work. A small thing we're doing in the software team is we do QA Wednesday afternoons, where we'll try to actually reduce the technical debt that's been accumulated in our old applications by writing tests for them. And when we address bugs that are the highest priorities from the science divisions, we would on Wednesday afternoon write tests for them and refactor and document them and really try to improve the quality in a very targeted way. And then when they come back, we'll try to tackle some priority applications, and Tony Pack's got some ideas of what that might be, using this approach, and really see if we can get some runs on the board. And if this is a success, then we can expand that way of working. But obviously we'll have to see how it goes. So that is the end of the talk. I will just... why do I have a balloon there? So I will read some words of Bertrand Piccard, who you may know. He's a balloon skipper, but he's also the driving force behind the Solar Impulse plane that flew around the world on solar power. And he's a real innovator and thinker. And he says, he uses the balloon as a metaphor for change. And we are in a time of change here in GA, so I'll just read these words. A balloon skipper needs to understand that the atmosphere is made out of several different layers of wind, all of which have different direction. If we want to change our trajectory in life or in the balloon, we have to change altitude. In this metaphor, the balloon is subject to the airflow that propels it along, just as we are imprisoned by our certitudes, problems and destinies. Just as balloons can change altitude to find air currents that alter their direction of travel, so too can we elevate ourselves professionally, psychologically, philosophically and even spiritually in order to assume responsibility for the direction we are taking. However, to do this, we must learn to jettison ballast, as in a balloon. The ballast of dogmas, ingrained habits, beliefs, and other set norms that we think we need but just hold us down. Each time we allow ourselves to explore the vertical axis, we are pioneers, not just in the atmosphere as balloonists, but in life itself. So thank you very much for that.